All right, today we're going to be looking at section 6.3, exponential functions. This section is really important. You may not know how to use them very well, but they are used in everyday, day-to-day calculations with banks and consulting firms, when people giving loans and buying houses and cars. Part of this exponential function is involved. In this section, we will do four things. These are our objectives. We're going to evaluate functions. We're going to graph those exponential functions. We're going to define the number e, and we're going to solve exponential equations. Before we get too far into it, I do want to give you a scenario just to kind of show you how some of it works. So this is something I saw a while ago. Let's say that I'm going to give you a job. Okay, this job is going to last 30 days. And in this job, you can get one of two payment options. I can give you $500 a day, okay, and you'll work 8-hour days, and it'll just be 30 days. Or I could give you 1 penny the first day, and then double your salary every day after that. So I'm going to say equals 2 times the previous. Okay, 2 times the previous. All right, so if I grab and drag this, it should copy that formula. Okay, so that's going good. So these are the two payment options. I can give you $500 a day for 30 days. Let's just drag this down to 30. Or I can give you 1 penny the first 8 hours, 2 pennies the second 8 hours, 4, and so forth and so on, and I would double it. Just think for a moment, which payment option would you rather? The $500 a day or the 1 penny? Now, if you think about it, most people would probably jump for the 500 because sometimes you might not even make that in 2 weeks, depending on what the job pays. Minimum wage is going up, but you know, sometimes this $500 a day seems really good. So if we did this payment option, by the end of 30 days, let's get a sum total. Let's go to formulas and sum. It's going to add up that column. Okay, so at the end of 30 days, you get $15,000, which is really good. I mean, some people, again, depending on the job, may not make that in a year, but minimum wage has gone up. However, let's look at the penny option. What if you chose a penny? Nobody, that doesn't seem good because we like things fast, we like it quick, we like a lot. So if we did 1 penny a day, let's drag this down to, let's just say, halfway. So 15 days. After 15 days, your salary for that day 15 will be $163. Now, if I did a sum total from 1 to 15, you wouldn't even have made $500 total halfway through. It starts out really slow, and that's the way exponential does. But once it grows, once we get past this point, and you continue doubling that salary every day, let's just drive it down to 20. On day 20, you're making $5,000, and that's going to get doubled continually all the way to the end. So by the time we get to the end, the last day, on that 30th day, what is this number? 1, 2, 3, 4, 5, 6. You will have made $5,368,709.12 on the 30th day. The sum total, if you do the whole column, in that 30 days, 1, 2, 3, 4, 5, 6, you have made $10,737,418.20. Now, the important part of this is that you understand this is the way things work in life and school and everything. It starts out really slow, like maybe math has started out that way. It starts out really slow. It seems like you're not learning anything. It's taking forever to get concepts. But as you go each day and you start to continue to remember and study and practice, you will start to pick it up, and you'll start to pick it up faster and faster and faster until you're growth is exponential. That's what this is. So all this just to say, it has very real applications in day-to-day life. And just imagine if you miss one day, you know how you miss a day at school and you seem like you're lost. If you miss a day, say you won't get that 30th payment, then you missed out on $5 million. That's half of what you would have got missing on one day. So you can miss a lot in one day. But anyway, that's just a little example. I really thought that was neat. If somebody gives you that option, you take that penny and double it every day. So let's talk about some of the things we're going to see in this section. This first page is kind of giving you exponential notation. You have some number at the bottom called a base, and then you have a number at the top called an exponent. Here is what we're going to be doing to define the number e. They're kind of estimating, taking some number, raising it to the power of pi, and adding more and more digits. The more digits you have, the better the accuracy. Okay, my mouse is freezing. Okay, continuing on. So we're going to be going over laws of exponents. I won't be going over it in great detail, but you do need to understand laws of exponents from previous math courses. Okay, my mouse is freezing up. Okay, there we go. So whenever you see multiplication with the same base, you know to add. If you have a power to a power, you multiply. If you have two terms in parentheses being multiplied, raised to some power, that power will get distributed to each term. If you have 1 raised to some power, it's just multiplying 1 repeated times. It will just be 1. If you have a negative exponent, that negative exponent will move that term in the opposite location, which then will make that exponent positive. So it moves it down. And then if you have anything to the 0 power, that is 1. Hopefully, if you looked at those extra credit videos, you would have seen them talk about why this is. Okay, so here's what exponential function is. You might have some real number multiplied times another number raised to a power. C is the initial value. The base A is the growth factor. Notice that C cannot be 0 and that your A has to be greater than 0, has to be positive, and it cannot be equal to 1. That would just give you a 1, a linear function, would not be exponential. Continuing on, kind of want to point out a few things. Here's the theorem, good to look over. We don't use it a whole lot, but it's good to kind of know where things come from. Let me continue. We will be looking at tables and trying to figure out if it is exponential or if it is linear. So what you do is you find that average rate of change or the slope, the ratio. So notice the x are counting by ones, and when you do the y values, it went down 3, it went down 3, keeps going down 3. That's a constant rate of change. That will be linear. If you look at this example, again, x's are counting by ones, which help. And then the y value, it went down by 16 the first time, and then it went down by 8, went down by 4. It's not the same. So if you notice it's not the same, you can check to see if it's exponential by dividing these two terms. So if you take as you go down the table, you take this term divided by the previous term, 16 divided by 32, you get a half. If you do that all the way down, 8 divided by 16, you get a half. So the division is a constant ratio. Okay, the ratio is consecutive. Therefore, that indicates this is exponential. So that's what you would look for. Is the ratio consecutive, or is the rate of change consecutive? So that is one thing we will use and try that out. So this is another table. Now here's what the exponential graph looks like. Okay, this is f of x equals 2x. Exponential goes through the order pair 0, 1. It starts out flat and then it curves up and then grows really, really fast. Kind of like that example that we looked at in the Excel worksheet. Starts out slow, grows really, really slow, then all of a sudden it hits a point and it takes off. All right, so this is what the graph looks like. We're also going to be doing transformations of this graph. So depending on how large your base is will determine the steepness of your curve. As you can see, this is y equals x to the 6th versus y equals x to the 3rd. The 6 is growing extremely faster than the 3. Here are some properties of exponential functions, talking about domain, range, and some points that work and don't work. Let me go on. I want to find some equations. So notice we have two different graphs here. Let's look at these. This one is called exponential growth. Growth is when your base is greater than 1. It's going upward. Exponential decay is when your base is less than 1 but greater than 0, or 1/2. It also has the same adverse effect as if you were to flip this across the y-axis. So when you make x negative and you flip across the y, this is the image you get. It looks like decay. But when you apply property of exponents, you can see that these two would be equal. So we will also look at transformations of these with flipping, translating, stretching, and compressing. I do want to look at solving some exponential equations. So here's some more graphics. This is showing you like a shift, like the -3 just shifts it down 3. But we'll be looking at all those. So E is a number like pi, used for exponential. We use that quite frequently in exponential graphs. So here's part where they're defining E. Now we don't actually use this, but you do want to look at it and get familiar, or at least kind of have a little understanding of where it comes from. It's hard to follow this because it requires calculus, and we're only in college algebra. So it tells you in calculus, this is how it's expressed. But this is just an approximation showing you that as they add more digits, it gets closer and closer to the value of E, which is 2.718, and there's several other values. So just like pi, it's an irrational number that we use in exponential expressions. Here we go, talking about transformations. That will be a part of our solving process, and then we want to solve exponential equations. So what we will do is we will try to rewrite both sides as having the same base. So I will show you how to look up a power table. But we have 3 raised to the x plus 1, and then they have that equal 81. Well, we can rewrite 81 as 3 to the 4th power. So once you do that and the bases are the same, we're just focused on the exponents, trying to get those to be the same because the bases are already the same. So x plus 1 equals 4. That's what you're solving. And when you solve that, you get that x equals 3. So this is what you'll be doing, and then there'll be other applications. And then we will also solve these in a graphing calculator. Okay, I think we may see some, it says use a calculator right here. So they'll give you some value, we'll plug it in the calculator, and we'll solve it. Okay, so these are the topics that we're going to cover. I just kind of skimmed through and kind of gave you an overview of what's going on, and then you get to the problem. So without any further ado, we're going to go ahead and jump to my math lab and start solving some of this.